Hi, in this video, I will explain frequency modulation in Max MSP. Let's begin. Okay, so we start with a simple cycle at 440 Hertz and a DAC object. If we hear this, then that means we're good to go. Okay, we hear it. Awesome. Going to use Alt and drag, selecting, delete them. Okay, cool. Now I'm going to delete the argument and we're going to instead make a constant of 440. And we connect this to the cycle, which is pretty much the same because this thing is always sending a 440 float or number to cycle, and cycle reads that as frequency because it's connected to the frequency inlet, okay? And so let's hear that. Awesome, it works, okay? Now, what happens if I create an LFO, a cycle at 1 hertz? I multiply that by 100 and I connect that to that same frequency inlet. Let's hear what happens. Okay, we get some sort of siren sound, right? Because it goes like woo, woo. Well, so what's going on here? Basically, if you connect two signals to the same inlet, it is as if you were adding them, right? Summing them. So this is the same as this, as a plus object and connecting these two. It's basically the same. It will make the same result, right? Here we go. Cool. But what is actually going on? All right. So a good way to debug or to see our signals, because we can see the cables, but we don't see the numbers, right? Is to go to debug and add signal probe and event probe. That way, when you hover your mouse on top of the cables, you can actually see the, oh, well, you need to turn on the DSP. You can actually see the numbers, right? It says there 440, cycle goes from -1 to 1. There you go. And if it gets multiplied by 100, it is times 100. And then the result will be a sine wave. Let me lower the volume on that. The result will be a sine wave that goes from 340 to 540, right? Does this make sense? It's because, again, let's put this in comments. Cycle goes from -1 to 1. And that gets multiplied. So you multiply the extremes by 100. And that equals from -100 to 100, right? That's the output of this multiplication. And then you do another one right here. And now it's that thing that goes from -100 to 100. Well, add 440. And the result is, 340 and 540. There you go. Right? So that's basic frequency modulation, right? Now, if you add knobs to this, I'm going to leave it there for a while so you can read it. If you add knobs to this, you can have more precise control of the rate of modulation and the amount of modulation, right? So this 100 right now, this 100, that's the amount of modulation. If I were to change it to 440, this thing would go from 0 to 880, right? Because 440 minus 440, it goes from 0 to 880 hertz, right? Then I changed this to 10 hertz. It goes super fast, right? But those 10 hertz are not in this formula. They're another thing. They're just the rate in which it's oscillating between -1 and 1, which gets multiplied by 440 in this case, right? So we can add some dials here. So let's go over here and let's add dial. And if you click on this small triangle, you go to prototypes. You can change this to pitch. Sorry, you change this to frequency. There you go, frequency. And now this is the amount of modulation in hertz. So if we can also have another one for our LFO. And that's how you get FM synthesis, right? But now this is really similar to modulating the frequency of not only an oscillator but a filter. So what happens with a filter, right? Because this is really substantial that you know for a subtractive synth. If we do a sawtooth, let's say a sawtooth right here, and we do an SBF, a straight variable filter, with a cutoff frequency of 1000 hertz and a resonance of 0.5, right? And we hear that. Let's turn on the DSP. That's our simple filter, right? And now let's use one of these frequency things, and let's use the pack F20 and the line trick, because we need to convert from data to frequency. Then we have a basic low pass filter. That's great for subtractive synthesis, right? Now let's imagine that we want the LFO to control that frequency and go whoop, 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 whoop. So how do we do it? It's basically the same algorithm as the one that I showed you earlier with the oscillator. You just simply have to, right? So have a cycle, and that gets multiplied by a frequency modulation amount, and that gets added to the cutoff frequency here, right? So it's pretty much the same, right? So again, this is the cutoff frequency in this case, and this one right here is the frequency or modulation amount, right? And this other thing right here is the LFO rate. This is the LFO rate. But it's pretty much the same. It's the same math, right? So you have, I don't know, something that is at 440 hertz. And again, this is at 1 hertz, and this is 100 hertz. It's the same result. Only we're changing the cutoff frequency instead of changing the frequency from the oscillator, if that makes sense. So if I change this to 440, we actually get that sound, right? And well, that's pretty much it. Another good way to do the math that I showed you earlier is to, well, we have the signal probe, but we also have here on, if you go to numbers, there's this number tilde GUI that you can just plug to any output, and there you can see the values, right, that are oscillating. And you can connect this to any output and make as much as you want. So there you go. This should go from minus 440 to 440. This one should go from minus 1 to 1. and this should be 440 straight up. So there you can like visualize your numbers and do the actual math, so it makes sense in your head of what's happening, right? It's again, this is all about numbers. It's all about it's very deterministic, right? There's nothing random about this. So, well, I hope you learned something, and I'll see you on the next one. Peace.